course.
Okay. So yeah, let's do sort of a recap. Basically, we are studying formal logic, and we are beginning the study of formal logic by studying propositional logic. Let me just zoom in to propositional logic. Now, propositional logic is composed of two terms. One is propositional, which is basically like um, a form of saying a proposition. So we defined a proposition as a statement that can take on a truth value among, so it is a type of statement among other three other types of statements that can take on a truth value. The other three don't take on truth values. Propositions are the only kinds of statements that take on truth values. Logic would be the study of arguments and reasoning and all of that. And we defined an argument as a set of premises and a conclusion initially, but then uh, we looked at some examples, and then we revised our for initial definition of argument to mean a set of propositions such that at least one proposition is a premise and at least one is a conclusion. So a premise would just be one of the propositions, um, like in the set of propositions that form an argument. One type of proposition. The other type will be a conclusion. The conclusion is a proposition which you intend to prove, and premises are the propositions which you use to prove the conclusion. Is that
Yeah.
fine? Yeah.
So far, I'm following. Yeah.
Okay. Yeah. Basically, the set contains premises and a conclusion. The conclusion is the proposition that you wish to prove, and premises are the propositions that you use to prove the conclusion. So that's what a premise is, and that's what a conclusion would be. Um, we looked at arguments, and we looked at these like, okay, we have an argument would have three propositions. Like you can't have an argument which has like one of the one of the premises is not a proposition. Like that would not be an argument. Um, an argument would be it would be a set of propositions, and it doesn't really matter what truth value each of the propositions takes on. Um, all of them could be false, and this would still be an argument. um, all of them could be true, and it would still be an argument, and any mixture of that would also be an argument. And even if you have a single premise and a single conclusion, that would also be an argument. You could have multiple premises, you could have multiple conclusions, that would also be an argument. um, then we talked about a little bit of an analogy with math. So we talked about variables in math. So something like x equal to um, 2. That would be, so x is a variable. Similarly, in logic, we use letters to represent propositions. So for instance, P could represent this proposition, Q could represent this proposition, and so on. And each of the propositional variables can be like these are the sort of arbitrary. Like we generally, as a convention, we start with P, Q, and R, but you could just name the propositions like A, X, or something that's similar. Like for example, if the proposition is my jeans are blue, you can just name it as, you could just assign it B to signify blue, or something like that. Whatever makes your life easy. You could just use, like, it doesn't really matter what propositional variables you use, but you need to remember that a single propositional variable can only represent a single proposition. You can't do stuff like you know use the same propositional variables for two different propositions. So you can't be like P equals my hat is blue, black. Okay, black. And you can also not like, yeah, basically don't use the same propositional variables for two propositions. So like my hat is blue. So don't do this. Don't represent two different propositions with a single propositional variable. And then we introduced briefly what logical operators are. They are like arithmetic operators, like, addition, subtraction, division, and multiplication. In logic, we have these operators. And I guess we can start today's session with a discussion on each of the operators, and we can go from there. We can, yeah. Um, One sec. So we have logical operators, and I'm only going to be talking about the logical operators in propositional logic. There are other logical operators that come in other systems of logic, but right now I'm only going to be talking about those within prop logic. So there are two categories. A unary operator and a binary operator. So yeah, so here unary, the un refers to 1, and here the binary refers to 2. Can you guess what unary and binary means given this information?
So one operator or two operator, I guess. Like
Uh,
one function or two functions.
Close, but basically the idea is a unary operator goes with a single proposition, whereas a binary operator connects two propositions. So, for instance, so there is only one example of a unary operator, and that's the negation. And every other operator we have will be an example of a binary operator. So a disjunction, a conjunction, a conditional, and a biconditional. Okay, so roughly these are there are some others. There is the exclusive disjunction, but that's pretty much it. Like there are other operators, but I don't think you will need more than this. Um, and I'll tell you why later. Like, why do you not need more than these? We'll get to that at some point. Uh, but yeah, so let's start by talking
So,
about.
so before we go into this, if
Yeah.
someone just listening to this and they're wondering why is what we're doing useful,
Hmm.
could you just maybe briefly explain why prop logic and all of this stuff is relevant or what
Oh
it can be
yeah,
used?
yeah. So the idea is we engage in like sort of conversations or debates all the time, and it's like we try to communicate what our arguments are in natural language, but the problem with natural language is that it's not like, even though it allows for a lot of like, it allows you to put a lot of emphasis on like, um, the emotion and stuff like that. It's really hard to kind of um, condense the like, you can have like long paragraphs, you can read long paragraphs of something that is a supposed argument while not understanding what the form of the argument is. Like, I can say stuff like, I can give you an example of an argument. I like, when you read a paragraph, there are like a lot of propositions scattered in the paragraph, but it's not clear how the conclusion follows from those propositions. So, what formal logic or propositional logic allows us to do is we can examine the relations between these propositions, and we can show whether the conclusion actually follows from the premises or not. And if the conclusion actually follows from the premises, then we get an opportunity to evaluate the premises themselves to see if they are true. Because if all the premises are true and the conclusion and the conclusion follows from the premises, then the conclusion has to be true by definition. So what formal logic gives us is a way to sort of symbolize a sort of an argument, like formalizing an argument such that the inference structure is very clear. Like, if I spam you with a paragraph, the inference structure might not be clear, but if I give you sort of an argument that is valid in propositional logic, which we will discuss, like what validity is, what soundness is, at some point we'll discuss that. But if I give you like a valid argument, you know exactly what the inference structure is of the argument, and then you can focus on attacking the premises. Because, yeah, I don't want to add more than that for now, because like, I want to get to the, like, we'll get to validity slowly. Like, validity and soundness are important concepts within propositional logic. But yeah, like, you could say something like, P1, it's raining. P2, I don't know. Or you could just go straight to the conclusion, like P2, um, therefore I should take an umbrella. You know, so basically, this is not it's not clear how this is following from this. Like, it could be true that it is raining, but it's not clear why I should take an umbrella if it's raining. But if I put this entire thing in a valid form, for example, I could just do P2. If it's raining, then I should take umbrella. I'll just write a U to save time. And then you have the conclusion as I should umbrella. basically take an umbrella,
Yeah.
you know. Now,
Hmm.
from this, the inference structure is very clear. Like, this is a modus ponens. So, like, this is P implies Q. So P implies P implies Q, P therefore Q. Like, I know exactly what the form of this argument is, and it's a valid argument. And then I can just go on to evaluate each of the premises. Like, is it actually is P implies Q true? Is P true? Stuff like that. I mean, yeah, the point just is, you are formalizing an argument such that the inference structure is not, um, obscure. Like, you are making the inference structure very explicit, and then you are examining the premises, and if needed you can request an argument for the premises. So it makes an argument really easy to deconstruct. So instead of like long Twitter battles or long rambling sessions on voice chat or whatever, we could simply just have like a formal argument on the table, uh, where the inference structure is really clear, and then you can just proceed with examining or attacking the premises. Uh, you could still do this in natural language. Like, there are some cases where in natural language the inference structure is very clear. In those cases, I don't think, um, it is really like necessary to formalize the argument. But when the inference structure is not clear, that's when formalization comes in. Like, whenever you are like, okay, I don't get the reasoning, that's when formalization comes in. If you're like, yeah, I know, like, I roughly know this person is saying, if it's raining, then I should take an umbrella. It is raining, therefore I should take the umbrella. Like, you can sort of get an idea that that's probably the argument from the natural language. Then you don't need to actually formalize it. You can go straight to like examining the premises, you know, and then proceeding from there. But yeah, that's what we get. That's why this is useful.
Okay. And when you said an argument for the premises, that's the same thing as examining the premises, right?
Yeah.
So
So
yeah. So
each premise is a proposition, right? So you could have an argument, right? You could have, let's say I reject this. Okay, I say I am not convinced that it is raining, and then what you could do is you can give me an argument where the conclusion is, therefore it is raining. Wait, I should write it more straight. It is raining.
so you're zooming in to the premise.
Yes, exactly. And then you have some premises like P1.1 or P1.2 something something, um, and then you have the conclusion, some premises, and then you have the conclusion. But the idea is, an argument for P1 should have P1 as the conclusion. So yeah, that's what I
So
mean
you
by an argument for a premise.
so you could keep on going in and in, right? So
Yeah.
then like so you could then do an argument for P1.2 or
Yes.
P1.1 and then zoom
If
in.
they are disputed, like if somebody, like, yeah, if it's like, if it's, if the truth value of the proposition is not clear, or like, or you think it is false, or if you're agnostic about it, um those, like, yeah, you can keep on going.
Cool. So, for example, when you're speaking with someone online and they they send you something which is a bit of gibberish,
Mm-hmm.
do you sort of try and formalize what you think they're saying and then ask them to uh
Sign off
well
on it.
send them Yeah, so do you write it out as how you feel it is and then ask them if that's what they mean?
Yeah, I generally do that these days. Unless it's like I mean, yeah, like even if it is very clear, I just write it explicitly so that I can like so there is no room for sophistry later on. Like they shouldn't be like, oh, I didn't agree to like agree that this is the correct interpretation. So I would just be like, okay, look, this is the like whatever you've given me is not like in a form, so I've just put it in a valid form for you, and now all you need to do is to tell me whether that's an accurate representation of what your argument is. If they say yes, then there's no turning back from there. Like they can't go on later like saying that, oh, this is not my argument, like you already signed off on it, and now like
Cool.
they're committed to defending the argument that they signed off to being an accurate representation of their argument.
Cool. And then someone who's being a sophist, which you said sophistry, that's just someone who's being uh, dishonest. Is that how you define that?
Yeah, like there are certain patterns that you will notice, like people um they'll try to like there are certain dishonest tactics in the sense that they'll affirm something and then they'll try to like, and when they see it going down to like whether when they see themselves contradicting or whether they're on the road to being shown to be false, they'll just like go back and try to reword whatever they said initially, um, or they'll try to like shift the burden of proof on you. All those kinds of tactics, roughly, they come under sophistry.
Okay.
Yeah.
All right then. So I guess we can move on to the operators, I guess.
Yes. So let's start with the negation. Uh, I'll just zoom in a little bit. Yeah. So negation. So negation is also called the not operator.
And it's a unary operator.
Yes, not is a unary operator. It is represented by a bunch of symbols. Um, you can do a negation. This is the standard like logic symbol, negation. You can do a tilde. This is the one that you find on your keyboard above the tab button.
Yeah.
Um, some like programming folks also use an exclamation mark. So any of these symbols should be fine. Um, yeah, and we are going to introduce another concept, a concept of truth tables, because to actually understand what each of these operators are doing, it's better to have like a bird's eye view of what's happening. Um, so when we say P is a proposition, what do we mean?
So it takes on the truth value. It can either be true or false.
Exactly. So if I put T in a table and I list out all the possible values, what would it be?
So it can either be true or false.
It can be
So,
true or false. Exactly. So we have P here, and then we have true, and we have false. These are the two probabilities. It can either be true or it can be false. And since negation is a unary operator, uh, there are only two, options. It can only be true or false. So when we do not P, what this operator basically does is flip the truth values. So it could be, so if this is true, then this will become false. If this is false, then it will become true. Basically just the opposite truth value of whatever truth value is in the column. You see what I mean?
Mm-hmm.
Yeah. You can also build the same truth table with ones and zeros. If you're into computer science, that's basically binary code. Um, you can have P and you can have not P. Um, so this will be 1 and 0. So true is represented by 1, false is represented by 0. What will not P be over here?
So there will be 0,
Okay, and this?
1.
Okay, cool. So yeah, so these are truth tables. And what they do is they document all the possible truth values that a given proposition can take. Uh, Documenting truth values. A truth table can also be used to you know assess whether two propositions are equivalent. um, we'll get there. We'll build on this later on. But yeah, that's basically what a not operator is. That's all it is. Like all it does is it takes the truth value and converts it to the opposite truth value. Okay, so you can also think of logical operators in terms of like circuits. So for example, if you have this, um, let me just do it over here. So let's say you have a circuit. Okay, and say I connect it to a power source. Um, Power source. This will turn on, right? But if I connect a not gate or a not operator, um, and then I try to power the circuit, then it will not turn on. So if this is 1, this will be 0. Just a sec, my obsidian is wilding. If this is 1, this will be 1. But if this is 0, then this will be 1. So yeah, you can just look at the not operator as basically like switching what um, truth value you are providing it. If you give it a 1, it will turn it into 0. If you give it a 0, it will turn it into 1. Then we can move on to the second one, and the first binary operator.
Disjunction.
It's a disjunction. Yep. So the disjunction is also called the OR operator. and this is represented with also like a bunch of symbols. Um, the most standard is the well. It's the V. It's sort of like a V symbol. You can also use a regular V. Um, I have seen some people use a slash, but a slash is not a particularly good operator to use because a slash is also used in set theory, like to represent complements of sets or something like that. Yeah, I think for a complement, a slash is used. But yeah, it is like people use different symbols for the OR operator, and this is the first binary operator. Connects two propositions. Okay. Can it connect three?
No, I'm guessing
Yeah.
because
You can't connect two. You can't connect more than two because it's a binary. You can't connect less than two because again it's a binary operator. Uh, so you can have like an example, right? So what you can do is there could be P or Q. So the operator falls between two propositions. You can connect three propositions in the sense that you can do like a P or Q or R, but that's still like it's still between two propositions, not three propositions.
yeah.
And to understand what the disjunction is, you could just think of it as like we could first look at the truth table. Okay, so that's the truth table. I'll just make the stuff more cleanly so that it's better. Okay, now uh, now instead of the unary operator, we now have like a binary operator. So we are dealing with um, two propositions. So there are different combinations that you can have between two propositions. So for example, when you toss a coin, right, it can either be heads or tails. But when you toss two coins simultaneously, you can have like one head and the other one also being head. You could also have the first one being heads and the other one being tails. You can have the first one being tails and the other one being heads, or you can have both of them show tails. So similarly, you can have the first one being true, the second one also being true, the first one being true and the second one being false, the first one being false and the second one being true, and both of them being false. Okay, so what you have now is four rows instead of the two rows that we saw in the previous operator. in the previous truth table, we now have 4, and this increases by a factor of 2 raised to n. So for example, over here, n will be the number of propositional variables. You see what I mean?
So if we have 2, it'll be 4 then.
Yeah, if you have 2 propositional variables, you will have 4 rows. Okay? So
So
these rows.
okay, so right now we've got PQ and P or Q, right?
Yeah,
So that's
but no. So we are talking about 2 propositional variables, not propositions. So this P or Q is a compound proposition. Compound proposition meaning it is made up of it's made up of 2 or more propositions which are connected using logical operators. So P or Q itself is a proposition. Okay. Do you get that? So when you have only 2 propositions, uh, you have, like, in the argument, if you only have 2 propositions, then you will have 4 rows. But if the argument contains more than 2 propositions, this number of rows will increase, because you're adding um the possible configurations in, like, for example, if you toss one coin, there are only 2 possibilities. It can either be true, it can either be heads or tails. But if you toss 2 coins simultaneously, you have 4 different possibilities. But if you toss 3 coins simultaneously, again you have more than 4. Like, now you have 2 raised to 3, which is 8 possibilities. So for example, let's say you have P, Q, R. So you could have all true, these two are true, and this one would also be true. Uh, this one false, this one true, and this one true. You can have this one false, this one false, and this one true. You could have this one true, this one true, and this one false. Just a sec. And then you have this one true, this one false, this one false, this one false, this one true, this one false, and then you have all false. You see what I mean? Like, if there are 3 propositions in the argument, then there are all of these different possibilities. You know,
yeah, and we'll get 8 rows, right?
you'll get 8 rows. If you count these, this will be 8 rows. 1, 2, 3, 4, 5, 6, 7, 8. So if you notice, we started from the unary operator that was 2 raised to 2. 2 raised to 1, which is 2. Sorry, one sec. And then we started with the 2 propositions. For 2 propositions, we had 2 raised to 2, which was 4. And then for this one, we had 2 raised to 3, which was 8. and for 4 propositions you will have 2 raised to 4, which will be 16, and so on. So the reason I told you this is because once you have more than 3 propositions, drawing truth tables becomes really cumbersome. So we'll be doing a lot of truth table stuff later on, which is why I sort of gave you like a warning, because whenever we have more than 3 propositional variables, we generally don't make a truth table. We look for other ways to evaluate arguments. Um, but as long as there are only two propositions or 3 propositions, it's fine to just make truth tables. Okay. Anyway, back to disjunctions. So the disjunction is basically going to look like this. So a disjunction is an OR operator, right? So for example, I'll just get rid of this so that you don't have to be okay, I'll just move it. Yeah.
To me, it seems that as long as one of them is at least true, then the disjunction is true.
Exactly. Exactly. So we can look at that with an example, right? So let's say we have a proposition. Um, okay, another thing of importance. I forgot to mention that in the negation thing. So whenever you have the not operator in natural language, you have certain motifs, um, which will tell you that a a logical operator is being used. So in case of a not operator, you will see stuff like not, it is not the case, one sec, and then it is like it is not, it's not true that. And you will also see it's false that. So for example, let's take we can take the proposition it is raining, right? And if I want to affirm the negation of the proposition, what will I say?
Uh, could you repeat the question? Sorry.
Yeah. So let's take the proposition it is raining as example, right?
Yeah.
Now that will be P. Now if I am to say not P, that will be not P, right? This is in
Yeah.
symbolic terms. What will that be in natural language?
It is not raining.
Yeah, that is one way to put it. You could also say it is not the case that it is raining. You could also say it is not true that it is raining. You could also say that it's false that it is raining. So all 4 of them represent the same thing. They all uh, mean not P. Okay.
Yeah.
Yeah. So these are like sort of like motifs, repeating patterns that you will see in natural language, which tell you that there is a negation symbol being used. So like when you are converting somebody's natural language speech or text to, uh, you know, a symbolic argument, you can look for these motifs to figure out what kind of propositions they are affirming in that speech, right?
Cool.
So yeah, over here also we could look at an example. Okay. So the example would be um, 8 is raining or I am dreaming or I am sleeping, whatever. Okay. So this entire thing is a proposition, right? Because it could be true or false that it is raining or I'm dreaming, right? The entire thing is a proposition. So the entire thing can take on a truth value. But whether this is true or not would depend on the individual propositions, right? So this is true. This is a disjunction. So you could, um, you know, symbolize it as P or Q.
Cool. Or pick more relevant letters, right? I guess like R or D. R.
Yes. Yeah, you have that option as well. You can either do that. You can just use a convention like P or Q, or you can be like R or D to make it easier to look at in a contextual sense. Like in an argument, it's easier to read R or D to mean the raining or dreaming. So yeah, you are free to pick whatever propositional variables you want. You don't even have to stick to the English language. You can use any you could use like a letter from Hebrew or something like that. Doesn't really matter what you use as long as it is agreed upon that that's the propositional variable that you're using. Um, yeah. So it is like, yeah, it is raining or I'm dreaming. So there are again um there are a few possibilities. This is true and this is true, which makes the entire thing true. This is true and this is false, but you're using an OR operator and at least one is true, so this is true. This is true. Sorry, this is false, but this is true. Again, at least one is true, so this will be true. This is false and this is false, which will make it false because both of them are true. So you're you're raining. It's raining or you're dreaming. If at least one is true, the disjunction is true, and I think you get the idea. As long as, yeah, that's how the truth table looks like. So even if at least like if even if one is true, the entire disjunction is true. A disjunction is only false when both the it, like so these are called this like each of them is called a disjunct. Okay, so these are both disjuncts, um, and both of them are atomic proposition. So atomic proposition in the sense, you know how like in chemistry atoms make up molecules, right? So you
Mm-hmm.
have like an oxygen, like O2 is a molecule. So you have O double bond O, is that correct?
Yeah.
Yeah. So you have like O double bond O, that's a molecule, but O itself is an atom. So similarly, here we have atomic propositions and we have compound propositions. where atomic propositions are like P and compound propositions are P along with some other proposition that is connected by a logical connector. So you can think of that as like an example. Uh, O2 is the molecule, or you could take the example of H2O. That's even better because there are uh, two atoms, um, or NaCl. That will be even better because there's one of each. One sec. So each of them is an atom, and the entire thing is a compound. Okay. So similarly, you have two disjuncts, um, and each of the disjunct is an atomic proposition, and then you have a compound proposition. So this entire thing is a proposition. Okay. Uh, Talking about the disjunction, there'll be certain motifs. There'll be certain motifs that talk about each of the, you know, like you could find them to be representing like a disjunction, right? So, um, let me see. I think it's only like an or either. Yeah. So, nat lang motifs. You have or either. So these are usually the kinds of natural language terms that you will find whenever somebody is trying to use a natural language. Whenever somebody is trying to give an argument in natural language. Okay. Um, so that completes the disjunction. You have any questions so far?
No questions?
Okay. So yeah, I guess. Oh, I think we have run out of time. But I think let's do one more so that you have something. Uh,
Yeah, so just for people to be clear, when you say natural language, you mean when people are speaking online and right?
yeah, we are talking about something like English.
Yeah.
Um, so symbolic language is just like playing with symbols, but natural language is the actual proposition in question that people are talking about. Like when people are talking, we are not talking about like P and Q. We are talking about the natural language propositions that people are like, that P and Q are representing. Like P could be I like pumpkins or something like that, right? And Q could be I am a queen. So yeah, like the the only reason why we're using the variable stuff is so that it's easier for us to process these things, and yeah. So yeah, basically like speech and text. That's the kind of stuff when we talk about natural language.
Okay, cool.
Yeah. Let's do one more so that you have something like I can probably give you a few questions or something like that. Um, the conjunction. Okay, conjunction is again represented by a bunch of symbols. Um, this is the standard like and symbol. It's like an upward pointing arrow. Um, you can also use the ampersand, which you could find on your keyboard. People also use a dot, And this is not like a period, like a full stop kind of dot. It's the dot that's like, you can find it on your phone if you're using Google keyboard. You can go to like numbers and then go on symbols, and like on the top row you'll find like a dot. It's next to the square root symbol. So that's the symbol we use for a conjunction. So these are the symbols we use. Uh, okay. So let's see what the truth table for the conjunction will look like. I'll just copy paste the table for um, disjunction here, and we'll just change the um, symbol. Okay. So just from the term conjunction. Oh, conjunction is also called the and operator. Forgot to mention that. And okay. So just give me a sec. Yeah. Uh, just from the name itself, can you try to guess what this will look like?
So I'm guessing this one is only true if both of them are true.
Yes.
So only the true P and Q are both true, and then the rest.
Yes. Exactly. So that's what this will look like, and yeah, like did we? Yeah, you could try to like the same concept applies here. P and Q is also a compound proposition, and each of these is called a conjunct. So both of them are called conjuncts. So P is one conjunct, Q is another conjunct, um, and then you have the operator over here, of course, and then the entire thing is one proposition. So that will be sort of like a structure of a a conjunction. Then we'll see that natural language. Motifs. Can you think of any natural language motifs that would represent um, the conjunction?
Just and
Mm-hmm.
also,
Oh yeah.
in addition,
Mm-hmm.
as well as.
In addition, as well as. Hmm.
Can't think of any more.
Uh, there something like, oh, both. There are many. Point is, like, you'll sort of see motifs like these when people are talking, and you could use those to figure out what kind of operation they are performing on the proposition. Like, you could sort of try to guess the relation between the propositions. Uh, and yeah, I think that should be good enough for today.
Yeah, that's perfect.
Yep.
Learn a lot, and yeah, for if people listen to the last episode, the last time, last lesson, yeah, I asked you whether if someone calls someone by their wrong name,
Mm-hmm.
whether that's analytically false.
Yeah.
You've answered to me that no, that's not analytically false because words, names, they're just sounds, right?
Yeah. So it's like, when I say something is analytically true, it means that it is true just if I just look at the definitions of the terms. So, for example, if I say, uh, all bachelors are unmarried men, that proposition is just true in virtue of what a bachelor means. A bachelor just means unmarried man. But in terms of like your name or something like that, your name, the definition of your name is not Patrick. The definition of your name will be something like the sound or a string of characters that is used to um, refer to you. That will be what your name means. So from that, it's not clear that your name is not Ben. To actually establish that your name is not Ben, we would sort of need some kind of something more than just the definitions. Maybe some kind of like experience, like me interacting with you, you telling me that your name is Patrick and not Ben. That's the kind of stuff we will sort of be referring to when we are saying that this proposition is false, not just the definition.
Hmm. Yeah,
Yeah.
great.
Yep. So we covered three operators today. We'll cover the
I
conditional, biconditional, and exclusive disjunction tomorrow.
Yeah,
Not tomorrow. The next session.
next week. Yeah,
Yeah.
whenever it is.
Yeah. Whenever that is. Cool.
Cool. Yeah. Yeah, that's very useful. We covered quite a bit.
Yep. We're just getting started. Like, uh, right now we're just learning the rules of chess. To give you an analogy. Like, the actual chess strategies are yet to come. Like, and that's where the fun begins.
Mm, yeah. So afterwards, yeah, I hope I'll be able to use your different Discord servers because there's a lot of information there, and
Yeah.
hopefully people following as well, they'll be able to maybe get an idea of. I'm not sure if we'll be able to cover most of the stuff from your Discord server or not, but
Yeah,
hopefully.
I think we'll cover just like the structure of things there, but the content is another like ball game. Like some of that, like some if there's like going to be like philosophy stuff, um, then it's more of like being familiar with the positions and stuff like that.
Yeah, that'll be cool. And yeah, I also want to ask you at some point about some other stuff related to veganism. That would be
Oh
great.
yeah, yep,
Such as
absolutely.
odd order predators and stuff like this.
Yep,
Yeah, that'd be great to hear.
yep,
All right then.
yep.
So
Cool. I'll end the recording now.
perfect.